So in this video, we're going to look at our horizontal transformations of our sinusoidal function. So that's f of x is sine x and f of x is cos x. So we'll be looking at k in here and d. So first k is actually called the wave number when we're talking about it with sinusoidal functions. And we've seen what k does before in our unit on function transformations. We know that k does horizontal stretches and compressions. So k is going to do horizontal stretch. And if you remember, that actually happens, a horizontal stretch happens when k is in between 0 and 1. So k, when it's in between 0 and 1, that's when you get a horizontal stretch. We know that k does a horizontal compression. And that's when k is larger than 1. We also know that k can do reflections in the y-axis. You actually don't, that would be when you have a negative k value. We're not going to do that too much in this unit, but that would be also true. So if k is negative, you'd have a reflection in your y-axis. But there's one new thing that's really helpful about k, and that's for a sinusoidal function like sine or cos. K tells you how many cycles, so one full cycle for a sine function, maybe would start here, right? Goes up, comes back down, and returns to equilibrium again. So that would be one full cycle right there. How many cycles fit within 360 degrees? So the k actually tells you that. So k tells you the number of cycles that fit in 360. So that's why k is actually called the wave number. It tells you basically the number of waves in 360. And because of that, there's a really nice relationship between k and period, which is that k is 360 divided by the period, and then rearranging that same equation, the period is 360 divided by k, which is another really handy relationship. So here in this example, you've got a sine function I've already drawn for you, and we're trying to graph sine of 2x. So that means k is 2. Or in other words, there are 2 full cycles of a sine function. Within 360. So what you want to think about is look at that base shape of a sine function, right? A sine function starts at an x-intercept, has an x-intercept in the middle, and ends at an x-intercept. Halfway in between those first two x-intercepts, there's a max. Halfway in between the second two x-intercepts, there's a minimum. So that is the shape of a sine function. That right there, sort of the shape that you're looking at. What we need to do is take that shape and fit 2 of them within 360. So what you want to do is map that out. So one's going to fit in here, and one's going to fit in this space here. So in this first space between 0 and 180, I would have to start with an x-intercept, end with an x-intercept, have an x-intercept in the middle. And halfway in between those first two x-intercepts, I need a max. The max is at 1 here. Halfway in between the second two x-intercepts, I need a minimum. And that is one sine function right there. The next one starts at an x-intercept, ends at an x-intercept, has an x-intercept in the middle. Halfway in between the first two x-intercepts is a max. Halfway in between the second two is a minimum. That is my second sine function. Do the same thing here. So I need to fit 2 within 360. So there'll be 1 in here and 1 sine function in here. So I started at an x-intercept and an x-intercept, have an x-intercept in the middle. Halfway between the first two x-intercepts is a max. Halfway between the second two x-intercepts needs to be a minimum. There's 1 sine function, and then the same idea here. So what you'll notice is there's 2 sine functions within 360. That's because k is equal to 2 here. All right, now here's k being equal to half. So that's going to mean a horizontal stretch by 2. Or another way to think about it as half of a sine function, because this is a base sine function here. will fit in 360. So what I need to do is look at just half of a sine function. I'm essentially taking this part of my sine function, just that first half, and I'm going to stretch it out over 360 degrees. All right, so that first part of a sine function starts at x-intercept and it ends at an x-intercept, and halfway through the middle is a max. So halfway here we need to put our max, and that right there must be the first half of a sine function. Now to do the same thing to the negative side, so I'm taking this piece, half of my sine function, and I'm stretching it out over 360. So starts at an x-intercept, ends at an x-intercept. Halfway in between, I need to get to a minimum. So that must look like that. And that right there is our graph of sine of a half x. Okay, here's one where I have a picture and I need to figure out the equation. So the first thing you want to do is say, is this a cos or a sine? So remember, a sine function will have this basic shape of starting at equilibrium, going up and down and back again. So that's a sine function. A cos function will have the basic shape of starting at a max, going down and back to a max again. So that's a cosine. So here, what you can see is I'm definitely starting at equilibrium, going up, down, and back to equilibrium again. So this must be a sine function. So the first thing I'm going to do is just write f of x is equal to sine of something x. I don't know k yet, but I do know that it's a sine function here. I can see the amplitude is 1, so all of that will be normal. The shift upwards, the c value, the midline is at 0, so I don't need to worry about that. What I have to figure out is k. And here, if I had all the way through to 360, it would be easy. I could just count how many cycles fit in 360. But the graph kind of cuts off early, so I might need to use my formula. So my formula is that k is equal to 360 divided by the period. And for us here, looks like the period, so one full cycle, the time for one full cycle is 90 here. So the period must be 90. So I'm doing 360 divided by 90, and that is 4. So I get to put in k is equal to 4 here. So that would be my equation for this function here. All right, and one more. Let's say I'm given the equation and I want to know the period. Well, I can read k right off the equation. K is 2/5. And then you can use your equation for period, which is just 360 divided by k. So period will be 360 divided by 2/5. And that is 900. So the period will be 900 for this cosine function. All right, the next thing is phase shift. So phase shift is the d value in your equation. And if you remember from our transformations unit, d is a little bit confusing. So if you're subtracting a value inside your sine function, so if you have, or your cos function, same idea. So if you have, say, f of x is sine of x plus some numbers, maybe say plus 30. That means slide to the left by 30. And that's horizontally, right? So that's a horizontal slide. If you have subtraction in there, so sine of x minus 30, you want to slide right by 30, also horizontally. So phase shift, or D, is a horizontal slide. Just watch out, same as before, the signs are a bit confusing, right? So if you have a plus a number in here, you're going to slide actually backwards. And if you have a minus number, you're going to be sliding forwards. Right, so here's an example. Let's see, we have the purple function is the thing we're trying to model. The red function is a sine function. You can see it's a sine function because it starts at equilibrium. goes through 180 and 360 at equilibrium again, has the maxes and mins that we'd expect of a sine function. But what we can see is that clearly the purple function has been slid forward. And it's been slid forward by, it looks like 90 degrees, right? This point slid forward 90, this point slid forward 90. Every point on that red function has slid forward to make the purple function. So when I'm trying to model the purple function, I'll start with the base sine function, but then I have to indicate sliding forward by 90. So sliding forward is actually minus 90. So the purple function would be sine of x minus 90. So here's another one where it's been slid backwards by 90. So you can see that the red function is a sine function. The purple function in this case is actually a cosine. Notice, right, cosine starts at maxes, ends at the max, goes through 90 and 270. So that is already a cos function. So you could call that purple function just cos of x. But you could actually write it as a sine function as well that's been slid. So a sine function and a cos function are actually the same shape. They're just slid over with a phase shift, with a d value. So notice how far it's slid. It's also slid 90. So that point slid backwards 90. That slid backwards 90. So we could rewrite this as the purple function is going to be a sine function that has been slid over to the left by 90. Now, if you want to be really creative here, you can notice you didn't actually have to slide left. We could have taken the red function actually and slid it forwards by quite a lot. We'd have to slide this point forward all the way over to here, so that's 270. This point would have to slide all the way over there. This point would have to slide all the way over there, but that's still possible, right? So if I want to model it that way, I could say the purple function is sine of x minus 270. I've now slid everything forward by 270. And those are the same thing. Those are both models of the purple function. All right, one last thing is just to remember to factor out the k. So basically remember that your general form is going to look like this. F of x is a sine of k x minus d plus c. Notice the k is factored out. Or this could be a cosine in here, same idea, but the k is factored out. So you'll want to remember to do that. So in this case here, if you see something like this, notice that k has not been factored out yet. You need to rewrite that. So instead of just leaving it as f of x is negative 3 cos of 2x plus 60, we keep all of this stuff inside the cos function. We just have to factor that 2 out. So instead of being 2x plus 60, it's actually going to be 2x plus 60 divided by 2 would be 30. So when you factor a 2 out of there, you would be left with 30. That's just important for writing down your phase shift. Your phase shift is not 60 here. All right, so then in this example, the wave number k is just going to be 2. The period is 360 divided by k. So that's going to be 360 over 2, which is 180. So the period of this function will be 180. And the phase shift d is going to be this value in here. Kind of confusing with the sign. If we have a positive here, we'd write d down as like negative 30, but what that means is it's a slide in the backwards direction or to the left by 30. Really important thing is that you know sort of like what's physically happening there. So this is a slide backwards by 30.